Let's follow one order as the system grows. Checkout has just accepted order 42. Shipping needs to know about it. So do inventory, notifications, and analytics. Checkout starts by calling shipping directly. Create a shipment for this order. One service, one connection. Simple enough. But then inventory needs the order. Notifications needs it too. And so does analytics. Every new team adds another direct contract back to checkout. Each contract brings its own timeout, retry policy, error handling, and deployment coordination. The same integration work is repeated on every connection. What happens when shipping slows down? Checkout waits, retries pile up. A problem in one downstream service is now delaying the original customer request. That's the real cost of direct coupling. Change one consumer and the producer may have to change with it. 4 consumers now mean 4 contracts and 4 separate failure policies. Kafka changes the shape of the system. Instead of calling every reader, checkout appends the event once to a durable log. Each interested service can then read that event independently. What moves through Kafka is an event, a fact that has already happened. In our example, order 42 was created for customer 101. Checkout is the producer. It appends this event to the order events topic. Kafka places the record at the tail of one partition and gives that position a number, offset 3. Those topic partitions live on Kafka brokers. For fault tolerance, a partition can have one leader replica and follower replicas on other brokers. Each follower copies committed records from the leader. Shipping can read order 42 right away. And notice, the event stays in the log after it is read. Analytics can read the very same event later from its own position. Shipping and analytics never have to move at the same speed. Kafka keeps records according to a configured retention policy. Reading a record doesn't normally delete it. Retention or compaction determines how long that record remains available. So the core model is straightforward. Append the event, retain it, and let independent readers consume it at their own pace. Kafka organizes related events inside a named topic. Ours is called order events. Think of a topic as the logical stream that producers write to and consumers subscribe to. Behind that topic are partitions. Each one is an ordered append-only log. New records go to the tail. They are never inserted into the middle. Let's build a Kafka record. The value carries the event itself. Order 42, status created. The timestamp says when it happened. Optional headers carry metadata, source equals checkout for example, and the key identifies the related entity. Here that's customer 101. The producer's partitioning rule uses that key to choose a partition. In this example, customer 101 maps to partition 1. The complete record is appended at the tail of that partition. Kafka assigns its next position, offset 3. That offset is not a global event ID. It is only a position inside one specific partition. Partition 0, partition 1, and partition 2 can each have their own offset 3. Why split a topic into partitions? Parallelism. Each partition remains its own ordered lane, while several lanes can store and process events at the same time. When a record has a key, the producer normally feeds that key into its partitioning rule. Customer 101 keeps mapping to partition 1 as long as the partition count and the rule stay the same. That customer's order created event enters partition 1 first. The order cancelled event arrives later in the same partition. A consumer C is created before cancelled. Customer 202 might map to partition 2. Its events can move forward even while partition 1 is busy. This is the boundary to remember. Kafka preserves order within a partition. It does not promise one global order across every partition in the topic. but keys can distribute traffic unevenly. If one popular key sends most records to partition 1, that partition becomes hot while the others still have spare capacity. A useful partition key balances two needs: keep related events together when order matters, and spread traffic well enough to use the cluster. So, how is the topic read? Consumers doing the same job join a consumer group. Our fulfillment group is one logical subscriber backed by several workers. Within that group, each partition has one active owner at a time. A worker can own several partitions, but two workers in the same group do not actively share one partition. Add a third worker, and Kafka can assign one partition to each worker. All three partitions can now be processed in parallel. Add a fourth worker though, and there is no partition left for it to own. It stays idle. More consumers than partitions do not create more parallelism. Fraud detection is a different job, so it gets a different consumer group. It can read the same topic without taking any partition away from fulfillment. Each group commits its own next offset, the position where that group should resume. On partition 1, fulfillment may have committed offset 42, while fraud has committed offset 17. If the log end offset is 50, fulfillment is 8 records behind, and fraud is 33 behind. That gap between the log end and a group's committed next offset is consumer lag. A healthy consumer group starts with a stable assignment. Here, 3 consumers each own one partition. Then consumer 2 stops sending heartbeats. Partition 1 no longer has an active owner. The other assignments remain visible. The group coordinator starts a rebalance, giving the remaining members a valid new assignment. How disruptive is that rebalance? It depends on the configured group, protocol, and partition assigner. An eager rebalance revokes every assignment first. Cooperative rebalancing can move only the partitions that need to change, which reduces the pause. In this group, partition 1 moves to consumer 1. At no point do two active members own it together. The new owner loads the group's committed next offset 42 and resumes from record offset 42. But suppose the old consumer processed record 42, then failed before committing the next offset 43. The committed offset is still 42, so Kafka may deliver that record again after reassignment. That's replay, and duplicate processing is possible. An idempotent consumer makes the retry safe. Process order 42 again, and it still creates only one shipment, the same correct result. If you remember only 3 things, remember these. Producers append facts to one durable log instead of calling every downstream service. Topics are divided into partitions. Those partitions define both the ordering boundary and the available parallelism. Consumer groups divide partitions among workers, while separate groups read the same topic independently. But Kafka is not automatic reliability. Watch for hot partition keys. Monitor consumer lag. Design consumers to tolerate replay and duplicate processing. And remember that membership changes can trigger rebalances. Kafka is a strong fit when many systems need durable asynchronous access to the same event stream, and those systems move at different speeds. If Kafka is easier to picture now, you'll find deeper engineering guides and role-specific career paths at crackingwalnuts.com. Follow Cracking Walnuts for the next visual breakdown.